Namaskar, I welcome all of you to my YouTube channel. This is lecture number 34 on complex analysis. Today I am going to teach you how to evaluate the improper integrals of this type. Integration minus infinity to plus infinity f of x into dx. Here one important point is that this function f of x contains the polynomial terms only. Now let us learn how to evaluate this type of integrals. Students, to evaluate this type of integrals, we have to follow total 4 steps. In step number 1, we have to change the variable from x to z so that we can obtain an integral in terms of z only. Here C is a curve consisting of real axis from minus r to plus r and upper half of the circle modulus of z equal to r. That means the radius of the upper half circle is capital R and the center at z equal to 0. Next, move to step number 2. According to step number 2, we have to find out the poles and then extract the useful poles. Students, here the useful poles means these are the poles that are lying on the real axis and upper half of the circle. For example, we have total 6 poles. The location of the first pole is at this point, location of the second pole is at this point, location of the third pole is at this point, and location of the fourth pole is at this point, location of the fifth pole is at this point, and the location of the sixth pole is at this point. So according to the definition, the useful poles are z1, z2, z3 and z4, because these are the poles that are lying on the real axis and upper half of the circle. So useful poles are z1, z2, z3 and z4. Okay? Next, move to step number 3. According to step number 3, we have to find out the residues at the useful poles. So in our case, we have to find out the residue at z equal to z1, comma, at z equal to z2, comma, at z equal to z3 and residue at z equal to z4. Okay? Finally, let us move to step number 4. According to step number 4, the value of this integral is given by twice pi iota into sum of residues at the poles lying in the upper half of the circle modulus of z equal to r plus pi iota into sum of residues at the poles lying on the real axis from minus r to plus r. So according to our example, the value of this integral is given by twice pi iota into sum of residues at the poles lying in the upper half of the circle modulus of z equal to r. That means residue at z equal to z1 plus residue at z equal to z2. Residue at z equal to z1 plus residue at z equal to z2 plus pi iota into sum of residues at the poles lying on the real axis from minus r to plus r. That means residue at z equal to z3 plus residue at z equal to z4. Residue at z equal to z3 plus residue at z equal to z4. Okay. Now let us solve one numerical problem to understand the theory part. Problem number 1. According to this problem, we have to evaluate this integral. So solution to problem number 1. So given the integral I is equal to minus infinity to plus infinity 1 divided by x to the power 4 plus 1 into dx. Next, we have to change the variable from x to z. So after changing the variable from x to z, we will get integration along curve C 1 by z to the power 4 plus 1 into dz. So here we have seen that we get an integral in terms of z only, and this integral can be written as integration along curve C f of z into dz, where f of z is equal to 1 by z to the power 4 plus 1, and C is a curve consisting of real axis from minus r to plus r, and upper half of the circle modulus of z is equal to r. Next, we have to find out the poles. We know that poles can be obtained by putting the denominator equal to 0. The poles of the function f of z can be obtained by putting the denominator equal to 0. That is, z to the power 4 plus 1 is equal to 0. So therefore, z to the power 4 is equal to minus 1. From this, we can write z is equal to minus 1 whole to the power 1 by 4. Next, let us express minus 1 in exponential form, that means in r into e to the power iota form. In our case, r is 1 and theta or argument of minus 1 is twice m pi plus pi. So therefore, in exponential form, minus 1 is given by e to the power iota into twice m pi plus pi. Students, if you do not understand how I am getting minus 1 as e to the power iota into twice m pi plus pi, please watch my lecture number 2. In that lecture, I had given detailed explanation on various representations of complex numbers. Now, let us substitute minus 1 as e to the power iota into twice m pi plus pi. So finally, we will get z is equal to e to the power iota into twice m pi plus pi whole to the power 1 by 4. So after simplifying, we will get z as e to the power iota into twice m pi plus pi divided by 4. Here m can take values 0, 1, 2 and 3. If we put m equal to 0, then we will get the first pole. If we put m equal to 1, then we will get the second pole. Again, if we put m equal to 2, then we will get the third pole. And finally, if we put m equal to 3, then we will get the fourth pole. Okay? So we have seen that z in exponential form as e to the power iota twice m pi plus pi divided by 4, where m can take values 0, 1, 2 and 3. Now let us find out the poles. When m equal to 0, then first pole z1 is given by e to the power iota into pi by 4. Next, apply de Moivre's theorem. So after applying de Moivre's theorem, we will get cos pi by 4 plus iota into sin pi by 4. We know cos pi by 4 value is 1 by root 2 and sin pi by 4 value is 1 by root 2. So the location of the first pole is at 1 by root 2 plus iota 1 by root 2. Next, let us find out the second pole. So, when m equal to 1, then Z2 is equal to 2s pi plus pi, that means e to the power iota 3 pi by 4. Next, apply de Moivre's theorem. Cos 3 pi by 4 plus iota into sin 3 pi by 4. We know that cos 3 pi by 4 is minus 1 by root 2 plus iota sin 3 pi by 4 value is plus 1 by root 2. Next, let us find out the third pole. When m equal to 2, then Z3 is equal to e to the power iota 4 plus 1, 5 pi divided by 4. Next, apply de Moivre's theorem. Cos 5 pi divided by 4 plus iota into sin 5 pi divided by 4. We know cos 5 pi by 4 is minus 1 by root 2 plus iota sin 5 pi by 4 is minus 1 by root 2. So, finally, we will get minus 1 by root 2 minus iota into 1 by root 2. Next, let us find out the fourth pole. When m equal to 3, then Z4 is equal to e to the power iota 2 into 3, 6, 6 plus 1, 7, 7 pi by 4. So, after applying de Moivre's theorem, we will get cos 7 pi by 4 plus iota into sin 7 pi by 4 is equal to cos 7 pi by 4 value is 1 by root 2 and sin 7 pi by 4 value is minus 1 by root 2. So, finally, we will get 1 by root 2 minus iota into 1 by root 2. Next, let us plot these poles on the eigenplane. The first pole Z1 lies at the first quadrant of the eigenplane. The second pole Z2 lies at the second quadrant of the eigenplane. The third pole Z3 lies at the third quadrant of the eigenplane, and the fourth pole Z4 lies at the fourth quadrant of the eigenplane. Again, we have seen that out of these 4 poles, only 2 poles Z1 and Z2 are useful poles because they are located in the upper half of the circle modulus of Z equal to R. So, therefore, we need to find out residue at Z equal to Z1 and residue at Z equal to Z2 only. Now, let me write these points. Here, the useful poles, here the useful poles are Z1 and Z2 only. Okay? Now, let us calculate the residue at the pole Z equal to Z1 first. In our case, Z1 is e to the power iota into pi by 4 or 1 by root 2 plus iota into 1 by root 2. For simplicity, I am going to consider Z1 as e to the power iota into pi by 4. So, residue at Z equal to e to the power iota into pi by 4 is given by limit Z tends to e to the power iota into pi by 4 1 divided by d dz of Z to the power 4 plus 1 bracket close. So, after simplifying this term, we will get limit Z tends to e to the power iota into pi by 4 1 divided by 4 into z cube. Next, let us put the limit here. So, after putting the limit, we will get 1 divided by 4 into z cube. So, e to the power iota into pi by 4 whole cube. So, after simplifying, we will get 1 divided by 4 into e to the power iota into 3 pi divided by 4. So, this term can be written as 1 by 4 into e to the power minus iota into 3 pi by 4. Next, let us apply de Moivre's theorem. So, after applying de Moivre's theorem, we will get 1 by 4 into cos 3 pi by 4 minus iota into sin 3 pi by 4. So, finally, we get residue at z equal to e to the power iota into pi by 4 as 1 by 4 into cos 3 pi by 4 value is minus 1 by root 2 minus iota into sin 3 pi by 4 whose value is 1 by root 2. So, this is the value of residue at the pole z equal to z1. So, we have seen that residue at the pole z equal to z1 is 1 by 4 into minus 1 by root 2 minus iota into 1 by root 2. Next, let us find out the residue at the pole z equal to z2. In our case, z2 is e to the power iota into 3 pi by 4 or minus 1 by root 2 plus iota into 1 by root 2. For simplicity, I am going to consider z2 as e to the power iota into 3 pi by 4. So, residue, so therefore, residue at z equal to e to the power iota into 3 pi by 4 is given by limit z tends to e to the power iota into 3 pi by 4 1 divided by d dz of z to the power 4 plus 1 bracket close. After simplifying this term, we will get limit z tends to e to the power iota into 3 pi by 4 1 divided by 4 into z cube. Next, let us put the limit here. So, after putting the limit, we will get 1 divided by 4 into e to the power iota into 3 pi by 4 whole to the power 3. So, after simplifying, we will get 1 by 4 into e to the power iota into 9 pi divided by 4. So, this term can be written as 1 by 4 into e to the power minus iota into 9 pi divided by 4. Next, let us apply de Moivre's theorem. So, after applying de Moivre's theorem, we will get 1 by 4 into cos 9 pi divided by 4 minus iota into sin 9 pi divided by 4. We know cos 9 pi by 4 is 1 by root 2 and sin 9 pi by 4 is 1 by root 2. So, therefore, residue at z equal to e to the power iota into 3 pi by 4 is 1 by 4 into 1 by root 2 minus iota into 1 by root 2. Okay? So, we have seen that residue at the pole z equal to z1 is this one, and the residue at the pole z equal to z2 is this one. Now let us find out the value of the integral. The value of the integral is given by I is equal to integration along curve C f of z dz is equal to twice pi iota into sum of residues at the poles in the upper half of the circle modulus of z equal to r. In our case, residue at z equal to z1 plus residue at z equal to z2. Residue at z equal to z1 plus residue at z equal to z2, bracket close, plus pi iota into sum of residues at the poles on the real axis from minus r to plus r. Here we have seen that there is no pole on the real axis. So, therefore, total residue is 0. Now, let us substitute the values of residue at z equal to z1 and residue at z equal to z2 here. So, finally, we will get twice pi iota into 1 by 4 into minus 1 by root 2 minus iota into 1 by root 2 plus 1 by 4 into 1 by root 2 minus iota into 1 by root 2. Here we have seen that this term and this term will be cancelled out. So, finally, after simplification we will get twice pi iota divided by 4 into minus twice iota divided by root 2, and finally, after simplification we get the value of the integral as pi divided by root 2. This is the answer. Finally, let me give you some numerical problems as homework. The problem says evaluate the following integrals. Number 1, integration minus infinity to plus infinity 1 divided by x to the power 6 plus 1 into dx. Number 2, integration minus infinity to plus infinity x square divided by x to the power 6 plus 1 into dx. Next, let me talk about a shortcut formula to solve this type of problems within 30 seconds. This shortcut formula will be helpful for those students who are going to appear various competitive examinations like CSI NET, GATE, SLATE, etc. in future. First, let me write this shortcut formula. Shortcut formula. Integration 0 to infinity x to the power twice m divided by x to the power twice n plus 1 into dx is equal to pi divided by twice n into cosec twice m plus 1 divided by twice n into pi. Now, let me solve these two problems by using this shortcut formula. So, solution to problem number 1. So, here given I is equal to minus infinity to plus infinity 1 divided by x to the power 6 plus 1 into dx. Students, here we have seen that this is an even function. So, therefore, this integral can be written as 2 into integration 0 to infinity 1 divided by x to the power 6 plus 1 into dx. For our case, m equal to 0 and n equal to 3. So, let us apply this formula. So, we will get pi divided by twice n, 2 into 3 cosec twice m, 2 into 0 plus 1 divided by twice n, 2 into 3 pi. So, these two and these two will be cancelled out. So, finally, we will get pi divided by 3 cosec pi by 6, and this cosec pi by 6 can be written as 1 by sine pi by 6, and sine pi by 6 value is 1 by 2. So, finally, we will get pi divided by 3 into 2, and after simplification we will get twice pi divided by 3. So, this is the answer. Okay? Next, let me solve problem number 2 by using this shortcut formula. So, solution to problem number 2. So, according to problem number 2, integration I is equal to integration minus infinity to plus infinity x square divided by x to the power 6 plus 1 into dx. Since this is an even function, so therefore, this integral can be written as 2 into integration 0 to infinity x square divided by x to the power 6 plus 1 into dx. For this case, m is equal to 1 and n equal to 3. Now, let us apply this formula. So, we will get 2 into pi divided by twice n, 2 into 3 cosec twice m, 2 into 1 plus 1 divided by twice n, 2 into 3 into pi. Here 2 and 2 will be cancelled out, and after simplification this term will become cosec pi by 2. So, finally, we will get pi divided by 3 cosec pi by 2 is 1 by sine pi by 2. We know that sine pi by 2 value is 1. So, 1 into pi by 3 value is pi by 3. So, this is the answer. Okay? So, this is all about today's video, and I hope that you have learned a lot from this video.